Assalamualaikum and good day. In this video, I will show you how to solve an LP problem using the Big M method. We need to use this method when there is at least an artificial variable in the tableau form. According to the penalty rule for artificial variables, the objective coefficient of the artificial variable is positive m in a maximization problem and negative m in a minimization problem. Here, m represents a very large positive number. Example, after we write the LP model in the tableau form, there exists an artificial variable in row 3. A3 is chosen as the basic variable for this row. Hence, we need to add MA3 to the row 0 to the objective function. That now, row 0 will change to maximize z minus 4x1 minus 3x2 minus 3x3 minus 8x4 plus MA3 equals to 0. This is a formal description of the Big M method. The first step is we need to make sure the right-hand side of each constraint is non-negative before we convert the model to standard form. And then, we need to find the basic variable for every row. An artificial variable is added to the constraint with no basic variable. Then, in step 2, we need to include MAI to the objective function. For maximum problem, we add positive MAI, but if the problem is minimize Z, then we add negative MAI to the objective function. Next, because each artificial variable is the starting basic variable, all artificial variables must be eliminated from row 0 before beginning the simplex. Finally, we solve the problem by the simplex method. We apply step 3 to 5 in the simplex algorithm. Now let's solve LP problem shown in example 3. This is a minimization problem with 2 decision variables and 3 constraints. Because none of the constraints has a negative right-hand side, we don't have to multiply any constraint through by negative 1. Then, we convert the model to standard form. For row 1, we add S1 to the left-hand side of the constraint. For row 2, we subtract an access variable, E2. And for row 3, we rewrite the whole constraint because it's already in equality form. Constraint 2 and 3, we require artificial variables. Then, we add an artificial variables A2 and A3 to both rows. Then, we write the sign restriction. We see that our initial basic variable will be S1, A2 and A3. For row 0, we transfer all variables to the left-hand side. Because we are solving a minimum problem, we add negative MA2 and MA3 to the objective function. Now, row 0 is minimize z minus 2x1 minus 3x2 minus ma2 minus ma3 equals to 0. The constraints remain unchanged. Next, we draw the tableau, the initial tableau. As we can see in this tableau, S1, A2 and A3 are basic variables. And we must remember that all basic variables have 0 coefficient in row 0. Therefore, we need to eliminate A2 and A3 from row 0. To eliminate A2 and A3 from row 0, we use row 2 and row 3, and we must multiply both row by m. Okay, therefore, to get new row 0, the formula is R0 plus MR2 plus MR3. Now we need to get the new coefficient in row 0. Okay, we get the new row 0 from this formula. Now we go column by column. Okay, for column Z, we only have one coefficient in row 0. Okay, next in column X1, we have negative 2 in row 0 plus m times 1 in row 2 plus m times 1 in row 3. Next, for column X3, X2, we have negative 3 plus 3m plus 1m. For S1, we have 0 coefficient. For E2, we have 0 plus negative m. For A2, we have negative m plus m, and for A3, we have negative m plus m equals to the right hand side. We have 0 plus 20m plus 10m. Next, we simplify this equation. We get Z plus in bracket 2m minus 2x1 plus 4m minus 3x2 minus me2, and there is no more coefficient, there is zero coefficient for A2 and A3, then equals to 30M. Using this new row 0, we update the initial tableau. So the coefficient for row 0 for x1 is 2m minus 2. Coefficient for x2 in row 0 is 4m minus 3. S1 has 0 coefficient in row 0. E2 is negative m. And both A2 and A3 have 0 coefficient in row 0. And the right hand side is 30m. Because we are solving a minimum problem, so the variable with the most positive coefficient in row 0 should enter the basis. Because 4m minus 3 is greater than 2m minus 2, variable x2 should enter the basis. Then we calculate the ratio. Ratio for row 1 is 16. Row 2 is 20 divided by 3, we get 6.7. And ratio for row 3 is 10. The ratio test indicates that x2 should enter the basis in row 2, which means the artificial variable A2 is the leading variable. Next, we update the tableau. Basic variable in tableau 1 are S1, X2 and A3. Others are NBV. We want coefficient of x2 in row 2 becomes 1. Therefore, we replace row 2 by row 2 over 3. The ERO for row 2 is R2 over 3. Okay, with this ERO, we get a new element for row 2. Now, we can eliminate x2 from row 0, row 1 and row 3. The ERO for row 0 is row 0 minus in bracket 4m minus 3 times R2. Okay, using this ERO, we can get coefficient for x1 in row 0. R0 is 2m minus 2 and minus in bracket 4m minus 3 times R2. R2 is 1 over 3. Then we simplify this, we get 2m minus 4 over 3m minus 2 plus 1. Therefore, we get equals to 2 over 3m minus 1, which is equals to 2m minus 3 over 3. Okay, we substitute, we write this coefficient in this cell. Using the same ERO, we calculate the coefficient of every variable in row 0. Hence, we get 0, 0, m minus 3 over 3, 3 minus 4 m over 3, 0, and right hand side is 60 plus 10 m over 3. For row 1 and row 3, the ERO for row 1 is row 1 minus 1 over 4 R2, and ERO for row 3 is R3 minus R2. Therefore, the new row 1 and row 3 is shown in this tableau. Tableau 1 is not the optimal tableau because there still exists positive coefficient in row 0, which is coefficient for x1 and e2. Since 2m minus 3 over 3 is greater than m minus 3 over 3, therefore x1 is the entering variable. Next, we calculate the ratio. Ratio for row 1 is 5.6. Ratio for row 2 is 20. And ratio for row 3 is 5. The ratio test shows that row 3 has the smallest ratio. Therefore, A3 is the leaving variable. To enter x1 into the basis in row 3, we replace row 3 by 3 over 2 R3. Thus, new row 3 will be 1, 0, 0, 1 over 2, negative 1 over 2, 3 over 2, and right hand side 5. To eliminate x1 from row 0, we apply ERO R0, R0 minus in bracket 2m minus 3 over 3 times R3. Now, x1, x1, x2, and s1 have 0 coefficient in row 0. Coefficient for E2 is negative 1 over 2. Coefficient for A2 and A3 are 1 minus 2m over 2 and 3 minus 2m over 2 respectively. The right hand side of row 0 is 25. ERO for row 1 is R1 minus 5 over 12 R3, and ERO for row 2 is R2 minus 1/3R3. Now, row 1 and row 2 are computed using these EROs. We can see here Tableau 2 is already completed. Because all variables in row 0 have non-positive coefficient, this is an optimal tableau. And also we can see coefficient for basic variable in row 0 is 0. S1 has 0 coefficient in row 0. Same goes to x1 and x2. All these basic variables have 0 coefficient in row 0. And also in this tableau, all artificial variables are equals to 0 because they are non-basic variable. Therefore, we have found the optimal solution to this problem. The optimal solution for this problem is x1 equals to 5, x2 equals to 5, s1 equals to 1/4, and e2 equals to 0. And the value for optimal Z is 25. That's all for now. Thank you.